To explore the universe, NASA relies on computing infrastructure split between two intensely hostile environments, the vacuum of space and the data centers of Earth. On the ground, the agency builds terrestrial supercomputing facilities engineered for absolute maximum throughput, running tightly coupled physics simulations at multi-petaflop speeds. In orbit, the engineering requirements completely invert. Systems are built for absolute operational resilience, bound by severe thermal fluctuations, strict power budgets, and constant threats of ionizing radiation. Ground systems seamlessly ingest petabytes of observational data from satellites to train massive artificial intelligence models. Beyond the protective shield of Earth's magnetosphere, spacecraft are forced to rely on fabrication nodes developed decades ago just to survive the harsh environment. This creates a severe hardware divide. How does an aerospace agency engineer a unified data lifecycle across two deeply contradictory computational spectrums? Bridging this gap requires merging these models, pushing autonomous edge computing far beyond low Earth orbit. This diagram shows Athena's internal node topology, prioritizing high core count x86 processors. It utilizes dual 128-core chips within a single node for embarrassingly parallel workloads. Expanding outward, 1,024 networked computing nodes achieve a peak performance exceeding 20 petaflops, 20 quadrillion operations per second. This dense processing capacity directly impacts physical engineering. When testing the Space Launch System rocket, Athena processes vast quantities of wind tunnel data to calculate vibrational physics, reducing computational analysis time from weeks down to mere hours. While deep space engineering relies on discrete physics equations, terrestrial climate prediction requires an entirely different methodology: continuous, massive-scale data assimilation. At the Goddard Space Flight Center, the Discover Linux cluster operates with a strict mandate. It must ingest and process 4 million discrete satellite telemetry observations every 6 hours to fuel global weather forecasts. This animation illustrates the system's four-dimensional data assimilation. The central atmospheric model requires a spatial resolution of 12.5-kilometer grid boxes, continuously plotting millions of incoming data points onto specific geographic intersections. To prevent bottlenecks during constant ingestion, the cluster relies on internal InfiniBand networks exceeding 56 gigabits per second, maintaining immediate communication between computing nodes. Earthbound models rely entirely on this flawless, uninterrupted hardware communication. Deploying silicon into space instantly removes that luxury. The primary threat to orbital computing is ionizing cosmic radiation. High-energy particles traversing the vacuum of space can easily penetrate physical spacecraft shielding. When an ionizing particle strikes a silicon microprocessor, it triggers a single event effect, physically flipping a binary state and corrupting data. This graphic compares transistor scales. Modern consumer CPUs use ultra-dense 3-nanometer nodes, highly susceptible to these strikes. To survive, aerospace engineers intentionally utilize physically massive 150-nanometer logic gates. The larger the physical gate, the more kinetic energy is required to alter its state. This requirement for physical size dictates the hardware. Missions like the Mars Perseverance rover rely on the rad 750 can withstand up to 1 million rads of absorbed radiation and operate flawlessly across temperature extremes ranging from -55 to +125 degrees Celsius. This resilience incurs a severe computational cost. The processor operates at a core clock speed of just 110 to 200 megahertz and utilizes a mere 256 megabytes of random access memory. Because the central processor is fundamentally bottlenecked at megahertz speeds, engineers must implement physical hardware bypasses to capture modern, high-resolution scientific data. Flagship missions face a severe data throughput problem. Modern optical sensors capture information much faster than the rad 750's limited memory bandwidth can natively read it. The James Webb Space Telescope illustrates this challenge. Its massive 6.5-meter primary mirror captures an immense volume of incoming infrared data, which is initially deposited into a 540-gigabit solid-state recorder. Instead of routing files through the internal computer, field-programmable gate arrays extract raw telemetry from the recorder. They dynamically insert communication headers and route the stream directly to the transmitter, entirely circumventing the processor to secure a 28 megabit downlink. The Europa Clipper mission employs a different physical workaround. Lacking central computing capacity for complex image stacking, the burden shifts to the spacecraft's physical optics. The Clipper utilizes an 8 megapixel sensor, constructed with massive 10 micrometer pixels. These larger physical pixels gather significantly more light natively, eliminating the need for the central processing unit to perform intensive image processing. Hardware bypasses secure massive data volumes for robotic probes. However, the computational architecture for human-rated spacecraft demands an entirely different standard of execution. Human-rated vehicles, like the Artemis Orion spacecraft, cannot rely solely on data throughput. They require architectures optimized for extreme hardware redundancy to ensure crew safety. Orion's avionics architecture is built on the principle of lockstep execution, utilizing a quadruple redundant system of computer modules. In this lockstep system, dual processors run identical flight software simultaneously, comparing outputs bit for bit. If a radiation strike causes a single discrepancy, the compromised computer initiates a fail-silent mechanism, severing its connection to the databus to prevent erroneous commands. Because of this automated isolation and reset protocol, the statistical probability of a total primary system loss is an incredibly minute one in 1.87 million. This rigorous hardware safety net is governed by real-time operating systems, specifically VxWorks. This software is designed to process data precisely as it comes in, guaranteeing strict execution timing down to the microsecond without unpredictable latency spikes. Absolute determinism prevents deep space hardware faults from becoming fatal errors. But the future of exploration requires moving beyond mere survival, pushing toward onboard autonomy. Deep space communication is strictly limited by the speed of light. This operational latency prevents Earthbound supercomputers from controlling distant rovers in real time. To solve this processing deficit, NASA is developing the PIC-64 HPSC processor. It replaces the single-core chips used for 30 years with a 10-core design capable of 100 times the throughput of current flight hardware. Unlike legacy proprietary systems, this processor is built on the open standard 64-bit RISC-V instruction set architecture, tapping into a vast global ecosystem of software tools and compilers. This graphic breaks down the new system on chip. It features a 10-core heterogeneous architecture, utilizing 2 management cores and 8 application processing cores. Crucially, these application cores integrate RISC-V vector extensions directly onto the die. These embedded vector units function similarly to a dedicated graphics card, delivering up to 1 teraflop of performance entirely dedicated to onboard artificial intelligence and machine learning inferencing. This leap in processing power allows engineers to deploy containerized, Kubernetes-orchestrated machine learning models directly onto these compact edge devices. Kubernetes is an open-source platform used to automate the deployment, scaling, and management of containerized applications. In practice, this enables profound onboard autonomy. An edge model could independently identify a distinct water ice signature in a lunar core sample, evaluate the data instantly, and alter the mission profile without waiting for Earth's intervention. By integrating raw processing power directly onto the spacecraft, NASA is decentralizing its architecture, turning orbital sensors into independent analytical nodes. Tracking these advanced orbital nodes requires a modernized terrestrial backbone. NASA has systematically replaced its Apollo-era mainframes with standardized commercial off-the-shelf server blades and gigabit Ethernet within its mission control centers. Across the agency, the massive NEST contract unified enterprise endpoints. Data scientists are now provisioned with localized high-performance hardware, like HP Z8 workstations, equipped with dual RTX 8000 GPUs, allowing them to train initial models at their desks and bypass supercomputer cluster queues. End-user computing extends directly into orbit. The International Space Station relies heavily on highly vetted commercial laptops, operating over a localized area network for daily crew tasks. However, the natural background radiation of low Earth orbit gradually degrades the commercial flash memory and delicate microprocessors of these laptops, requiring constant physical replacement via cargo resupply missions. To solve this logistical drain, NASA is prototyping a next-generation station laptop. They are mating the open-source Framework 16 chassis with a custom motherboard housing the new radiation-hardened HPSC processor. This modular architecture allows astronauts to physically swap, repair, and upgrade logic boards directly in microgravity, permanently defeating original equipment manufacturer vendor lock-in. Aerospace computing is no longer a strict dichotomy of Earth versus space. By merging terrestrial analytical capability with orbital edge logic, the future of deep space exploration is completely decentralized, highly autonomous, and inherently modular.